we should spend some time talking about super duper dangerous reactions. So most of the chemical reactions that we've talked about so far, we've been able to measure inside of a coffee cup style calorimeter, a calorimeter that's made of styrofoam. Now there's multiple styles of chemical reactions that we really can't put inside of a styrofoam cup calorimeter, like any combustion reaction at all. It just won't work. We won't have a coffee cup calorimeter at all anymore. So how do we measure the amount of heat that comes out of a more dangerous style chemical reaction? How do we actually stay safe and still measure that amount of heat? There's actually two ways that we can go about doing this. Number one, use a better calorimeter. This is what they would call a bomb style calorimeter. It's essentially the same thing, the same basic concept, where you have a giant pool of water, but this time the pool of water is contained inside of a metal jacket. And you'll notice that inside of it, kind of leading down from the ignition wires, there's something called a sealed bomb. Now that's quite literally almost like a little mini pipe bomb. It's a sealed capsule, and on the inside of it, a chemical reaction that is more dangerous is sealed up on the inside of there with lots and lots of oxygen. And we usually light it with a little electrical spark. And it goes kaboom. Now, the bomb itself doesn't explode, but the heat that's generated from the inside of that chemical reaction is allowed to ooze out of its own little sealed container and into the water that it's surrounding. And unfortunately, simply because of the name, we really can't use a bomb calorimeter on the inside of schools. So this is going to be something we'll kind of just theoretically talk about. This is also something we'll talk about yet again when you hit AP chemistry if you're going on for another year. So just again, one more time, the heat comes from the chemical reaction that takes place inside of this little container on the inside of the water. We call that the sealed bomb. And then the reaction's heat goes into the water that surrounds it. Not a super duper practical solution for us. So we need something else. And that something else for us is going to be called Hess's law. So say we're trying to go from reactants at point A to product at point Z. And what we do know is that the amount of heat that's involved with that process is tremendous. It's going to release a lot of heat energy very, very quickly, like a combustion or maybe even something almost akin to an explosion. We can't put that in a coffee cup calorimeter. So what do? Well, instead of going directly from A to Z, we're just going to take the reaction in small little increments. So maybe instead of going from A directly to Z, we go from A to B, and from B to C, and then finally from C to Z. And that each single one of those small incremental steps would take a lot less energy overall. Now, what Hess's law tells us is that this is perfectly allowed, and that the amount of energy that it takes to go down either path is going to be exactly the same. So if I want to know how much energy it takes to go from A to Z, I can add up the segments AB, BC, and CZ. So just simply add up the amount of energy that it takes to get from small step to small step, and that will equal my overall amount of energy. Now, although that's a fairly simple concept, the problems themselves look very complicated. And the next video is going to step you through the process of kind of the rules of the road of how do you do this? What does this look like?